Now let's see the reduction formula for integral 0 to pi by 2 sine power nx dx. That is, if I wanted to find integral of 0 to pi by 2 of sine power nx dx, where n belongs to positive integers and at the most n is greater than or equal to 2, then we have this equal n minus 1 by n minus 3 by n minus 2, n minus 5 by n minus 4, 3 by 4, 1 by 2 times pi by 2 if n is even. Then I have this equal to this, and this will be n minus 1 by n times n minus 3 by n minus 2 times n minus 5 if n is odd, is how we identify the two cases for finding integral 0 to pi by 2 sine power nx dx. If n is even, it is this times this times this, where the last term is pi by 2. If n is odd, then we have the same terms reduced to the last terms as 4 by 5 into 2 by 3 times 1. The cases of n even and n odd derives two respective formulae for integral 0 to pi by 2 sine power nx cos power nx sine power nx dx. Now, as we know that integral 0 to a f of x dx is integral 0 to a f of a minus x dx, and using this property, if I wanted to find integral 0 to pi by 2 of cos power nx dx, using this formula, this reduces to integral 0 to pi by 2 of f of a minus x, where a is pi by 2. So this reduces this. So the right hand side is substituted with the left hand side, and I get this. And as I know that cos 90 minus theta is sine theta, and therefore this reduces to 0 to pi by 2 of sine power nx dx. Therefore, integral of 0 to pi by 2 cos power nx dx will be integral 0 to pi by 2 of sine power nx dx. Both are equal. Is how we understand the two formulae connected. Integral 0 to pi by 2 cos power nx dx is equal to integral 0 to pi by 2 sine power nx dx. Therefore, since integral 0 to pi by 2 of cos power nx dx is equal to integral 0 to pi by 2 of sine power nx dx, we have the same formula which we have derived for sine as that for cos. That is, if n is even and if n is odd, where n belongs to z plus and n is at the most greater than or equal to 2, then we have this formula which is greater than 2. Then we have for n even, the formula is n minus 3 by n, so n minus 1 by n, and n minus 3 by n minus 2, so on and so forth till 1 by 2 times pi by 2 if n is even, and this will be n minus 1 by n minus 3 by n minus 2 times 2 by 3 if n is odd. Therefore, integral of this is equal to integral of this, which is this when n is even and this when n is odd. Now let's see the related problems. So in case of this, say for example, I have an example problem cos post 7x dx. So the question is to find this. Then clearly when I compare this with integral 0 to pi by 2 cos power nx dx, then I see that my n is 7, which is odd, and therefore taking the odd case of integral 0 to pi by 2 of cos power nx dx, which is n minus 1 by n minus 3 by n minus 2 of this is what we get in case of the reduction. Therefore, integral 0 to pi by 2 cos power 7x dx with n equal to 7 substituted here gives 7 minus 1, which is 6 by 7, and we observe that each of the terms of the numerator and denominator gets reduced by 2 units. So 6 by 7, next is 4 by 5, next is 2 by 3, which is the last term, and hence we halt here. And therefore integral of this is identified as this times this times this. When I cancel 3 1s, 3 2s, then I get 4 2s are 8, 8 2s 16, 7 5s 35. Therefore, integral 0 to pi by 2 cos power 7x dx will be equal to 0 to pi by 2 sin power 7x dx, which is 16 by 35, is how we identify integral of this equals 16 over 35. And even integral sin power 7x also is this, because they are equal. Now let's see the evaluation of integral with combination of m and n. That is, evaluation of integral 0 to pi by 2 sin power mx cos power nx dx. So let's see how we can evaluate this integral using the formulae. So there are different cases through which I can evaluate each of the integral. Integral 0 to pi by 2 has 4 cases. Totally 5 cases, 1, 2, 3, 4, 5, where I have 1, 2, 3, 4, and 5. So as we see each of the cases, let's come initially with n even and n odd. That is, if n is equal to 1, and then I take here with the condition m is equal to 1, then I have, let's see what happens for n equal to 1. Integral 0 to pi by 2 sin power mx cos power nx when n is equal to 1 is 1 by m plus 1. And here this is 1 by n plus 1, which we get by substitution method. Now similarly, if I take n not equal to 1 is odd, then let's see what will be the solution of this. If n not equal to 1 is odd, then I have this as n minus 1 by m plus n, and next the third case is n is even and m is even, and next is n is even and m not equal to 1 is odd. So these are the different cases 1, 2, 3, 4 and 5 through which we derive. For n equal to 1, the answer for this integral is 1 by m plus 1, and for m equal to 1, the answer is 1 by m plus 1, and for n which is odd or not equal to 1 is this minus 2, and so on and so forth by 2 by m plus 3, and then we get this to be 1 by m plus 1 is what we get in the final two values. Next is if m is odd, then in this case I have this as n minus 1 by m plus n, n minus 3 by m plus n minus 2, so on and so forth by 1 by m plus 2. Now therefore, in case of n is even and m is even, I have n minus 1 by m plus n, n minus 3 by n plus n minus 2, and so on and so forth till 1 by m plus 2, but continued m is even, therefore I have m minus 1 by n, and then next is m minus 3 by m minus 2 of 1 by 2 and pi by 2. Now clearly we see that this is the even condition of the previous session which we have seen in integral sine power nx or integral sine power cos or integral cos power nx with limit 0 to pi by 2. Now similarly this with m being odd comes as m minus 1 by m times m minus 3 by m minus 2, so on and so forth till 2 by 3 is what we get in that case. So we see that there are totally 5 cases of case 1, case 2, case 3, case 4 and case 5. With each of the case 1 the answer is this, and case 2 the answer is this, and each of the answers are with their respective m and n. But with the case 2 it is very important to note that if n is odd, this answer is irrespective of m, because for odd case m can be either even or odd. It doesn't affect, the formula is the same for m being either even or odd, but n has to be odd and not equal to 1 is a special case in case of all the 5 cases considered out here. Now let's see some related problems connected with this. So for this, let's take an example problem. Say I want to evaluate integral 0 to pi by 2 sine power 6x cos power 4x dx, and as I compare this with sine power mx cos power nx dx, I clearly see that my m is 6 and n is 4, and both are even, and hence we have both m is even and n is even, which is the third case, and let's see how we can expand using the case 3 of the formula. Integral 0 to pi by 2 So in order to evaluate integral 0 to pi by 2 sine power 6x cos power 4x dx with each of the even cases, then I have this with the formula m minus 1 by m plus n, n minus 1 by n plus n, and next is n minus 3 by n plus n minus 2, and so on and so forth till the last term which I get, and then taking the next pair starting with n even, I get m minus 1 by n and m minus 3 by m minus 2, so on and so forth till 1 by 2 and pi by 2 is what we get for the second set of numbers. So using this, it's easy to simplify when we just directly follow from the first term with each numerator and denominator reduced by 2 terms. Therefore, as I see here, my n, which is 4, is 4 minus 1, which is 3, and m plus 1, which is 10. Therefore, once the first value is evaluated as 3 by 10, substituting n and m respectively, then the next term is 2 terms short of 3 is 1, and the next term of 10 is 2 terms short of 10, which is 8. And then finally, you cannot proceed further because this cannot be reduced 2 terms shorter, which goes into the negative side of the numbers. So we halt here and then we go to m minus 1 by m. Similarly, m is 6. So using the formula 6 minus 1 by 6 is what we get in the initial term. And I see that each term is reduced by 2 units. Therefore, each of numerator is reduced by 2 units here, and next again the 2 units here, and of course pi by 2, which comes because it's an even case, is how consecutively each of the numerators and denominators are reduced by 2 units each time we proceed further. This on simplification gives us the whole of 3 1s, 3 2s, 5 1s, 5 2s is what we get. Therefore, this on simplification gives 3 pi by 4 2s are 8, 8 2s are 16, 16 2s 32, 32 2s 64 times 8, 6 8s 48, 512. Therefore, integral of 0 to pi by 2 sine power 6x cos power 4x dx is 3 pi by 512 is how we identify the integration. Now let's see about finding the areas using integrals. As we know that one of the main applications of integrals is in finding the areas, the question comes on how we apply the process in finding the area using integrals. Say for example, I have my x-axis and my y-axis, and say this is the origin, and I have 2 curves. The one given by y equals f of x, and I have another curve given by y equals g of x. Now as I see these 2 curves, I clearly see that f of x is the upper curve and g of x is the curve which is below. So we say that f of x is the upper curve and g of x is the lower curve. When we see this, this is upwards and this is downwards, and therefore This implies f of x is always upper of g of x, that is f of x is always greater than or equal g of x, but here it is strictly greater than. So in this case, this being greater than this is the condition through which we are going to define area between the bounds. So for example, I want to find the area between x equal to a, where the line cuts at a and which is perpendicular to x axis, and this is the line x equals b. Now using these two lines, we form a bound, that is, we have to find area of this region. Now how do we find area of this region which has the upper curve f of x, the lower curve g of x, the left bound x equal to a and the right bound x equal to b? Is what we connect with integrals. So this area can be found area of shaded region Therefore, area of shaded region is given by integral of the lower bound, which is x equal to a, and the upper bound, which is x equal to b on the rightmost. So integral of a to b, which is a definite integral of upper curve, comes always first, that is f of x, whatever is the upper curve comes first, minus the lower curve whole of dx, is how we define area of the shaded region using integrals, the definite integral. Integral lower limit to upper limit, upper curve minus lower curve of dx is how we define the area of the shaded region. Now let's see the general formula. That is, in general, area under the curve or area between two curves or the area of this shaded region is memorized as area equals integral lower bound, and here comes upper bound, and here comes upper curve minus lower curve of dx, is how we memorize the formula for area between two curves using definite integrals. So generally, for any curve, the general formula is derived as integral of lower bound, whichever lower bound is identified in the given problem, and the upper bound, and then the upper curve minus lower curve of dx. Now lower bound is always from left and upper bound is the rightmost. So here the leftmost boundary is x equal to a, and the rightmost boundary for the area is x equal to b, and the upper curve is f of x and the lower curve is g of x. Is how we identify the formula for area of the shaded region or area under the curves using integrals. Now let's see some special cases of finding areas. As we have seen, the general formula now comes on the different special cases through which we understand finding the areas of various types of curves. Say for example, I have my x-axis and I have my y-axis, and here is origin, and then and say I have the curve y equals f of x. I have only the curve y equal to f of x, and I have to find the area between the boundaries x equals a and x equals b. is what we're going to find out here. So in order to find this shaded region, we have only one curve, but the formula is for two curves. But here, as we identify that x-axis can also be taken as a curve, as assumed that equation of x-axis is y equal to 0. That is, this area is between the curves f of x and 0. So if I assume these two curves, then again the upper curve is y equal to f of x and the lower curve is y equal to 0, and the left bound is x equal to a and the right bound is x equal to b. So therefore, area under the curve y is equal to f of x is given by integral of lower limit, which is a, or the lower bound, which is a, and the upper bound, which is b, and upper curve. Clearly in this case the upper curve is f of x, therefore I have the upper curve coming first, and then the lower curve is x-axis, that is y equal to 0, because the area touches till x-axis. Therefore the lower curve is 0 times of dx is how we get. So if you simplify this, that implies area under the curve denoted by a is integral a to b is how we get area under the curve. So area under the curve y is equal to f of x is this f of x dx is how we understand for only single curve. Now let's see the next case of finding the area. So for example, I have the x-axis, the y-axis, and the origin, which we have out here. Now suppose instead of the curve in the first quadrant, what if the curve is in the third quadrant, fourth quadrant? That is, I have the curve y equals f of x down in the fourth quadrant, and then I have the boundaries x equals a and x equals b in this form. So how do I find area of this dotted region? Using integrals. So this comes as a special case of finding the area using the general formula, integral lower bound to upper bound, upper curve minus lower curve of dx. So let's see finding the area of this case using the general formula. Now as we see that the area of required region is clearly with the general formula integral of lower bound. We know that the lower bound is x equal to a and the upper bound, which is x equal to b, and here comes upper curve minus lower curve. Now as I see this area, x-axis is the upper curve, which has the equation y equal to 0. So upper curve is x-axis and the lower curve is y equals f of x. So the upper curve is 0 minus the lower curve is f of x over dx is how the general formula reduces in the case of the curve in the fourth quadrant as seen in the diagram. Now when we simplify this further, I get this to be integral a to b of minus f of x dx. Therefore, the area is given by minus integral a to b f of x dx is how we understand the area in case of the fourth quadrant. The area reduces to negative value, and negative sign indicates only the direction of the curve, but the area is always positive. So this is how we identify the cases through using the general formula, and in case of this, area of the required region is minus integral a to b f of x dx. Now next, let's see the next case of finding the area. That is, if I have the x-axis and the y-axis and I have the curve y equals f of x, and I have to find area of this shaded region. Now I have x-axis, y-axis and the curve y equals f of x. Then how do I find area of the shaded region where the x-intercepts of the curve are given as a and b? So in this case, we don't have the lower and upper bounds given, but we have the x-intercepts which help us in finding the area. That is, if I draw a line perpendicular to x-axis, and if I draw a line here perpendicular to x-axis passing through b, then clearly I see that these two bounds are x equal to a and x equal to b as taken from the x-intercepts of the curve. So therefore, we have the bounds between which I have the curve and x-axis. Now as I see this clearly, my left bound is x equal to a and my right bound or the upper limit is x equal to b, and my upper curve is y equal to f of x, and my lower curve is x-axis, which is y equals 0. Therefore, area of required region is integral lower bound to upper bound of upper curve minus lower curve dx. That implies area is integral a to b f of x dx. Is how we identify the formula for area of the shaded region using the bounds, indirectly using the x-intercepts. Now let's take the combined case where two cases arise as different issues in solving this type of problem. Suppose I have my x-axis and my y-axis, and I have this with say my graph here has this as x equal to a x equal to b, and it has x-intercept as c. Now I want to find area of this complete shaded region. So how do I find area of this shaded region using areas of integrals, or the general formula is the biggest question out here. So as I see this, this has two different areas which we're going to separately solve for and then add them to get the area this plus area this. So the idea behind is to find area of this, and when you add up, I get the area of the required region. So as I see this, I can see that there's an intercept C through which I can draw a line passing through and perpendicular. So clearly this line has the equation x equal to c because this line is parallel to y-axis. So I try to divide my region between these two bounds and these two bounds and then add up. So initially, let this be denoted by area A1 and this be denoted by area A2. So I see clearly from the diagram that in order to find area A1, it is nothing but integral of lower limit, which is x equal to a, and my upper limit, which is x equal to c. And here in this case of my upper curve is y equals f of x and my lower curve is x-axis, which is y equals 0. So I have f of x minus 0 dx. That implies a1 is integral a to c f of x dx, which I take as equation 1. Similarly, let's find area A2. Now A2 is nothing but integral of lower limit, which is x equal to c, and the upper limit, which is x equal to b. So x equals c to b. Now in this case, the upper curve is x-axis and the lower curve is y is equal to f of x. So the upper curve, which is 0 minus f of x dx, that implies A2 is minus integral c to b f of x dx is what we get as equation 1 and equation 2. Now in order to find the total area, we add A1 and A2, then we get the overall answer. Therefore, adding equations 1 implies A1 plus A2 would be integral a to c f of x dx minus integral c to b f of x dx. Therefore, area is integral a to c to b is how we identify the area using integral concept. Now let's see the special case, the next special case, which is, suppose I have x-axis and y-axis and origin through which there are two curves. Suppose I have two curves where one of the curve is given by the equation y equals f of x and the other given by y equals g of x. Then how do we find the area of the region bounded by two curves here? So as I see in this case, clearly we do not have the left and the right bound, or the lower and the upper limit, but I have clearly the upper curve, which is f of x, and the lower curve, which is g of x. So in case of this kind of a problem, we have to find the left and right bound, or the lower and the upper limit. So how do we find here? These two is the biggest question. So as we know that if I have a line passing through the point of intersection of the two curves here and point of intersection of two curves here, we have 2 points of intersections, one given out here and the other given out here. So points of intersections of two curves will help us in deriving the lower and upper limits. So as I draw a line perpendicular to x-axis and passing through this point of intersection, and as I draw another line passing through this point of intersection, then the x coordinate of the point of intersection will be the lower limit. Say my x coordinate of this point of intersection is A and this is B. So it is very important to note that in case of this kind of a problem, the lower limit is x coordinate that is least of the point of intersection. So lower limit is x coordinate of the point of intersection, that is the least, and the upper limit is the x coordinate which is the highest of the point of intersection. So when we get 2 points of intersection, this is this and this, say I denote the point of intersection here as A and here as B, then the x coordinate of A will define the lower limit and the x coordinate of B will define the upper limit. Therefore, in order to extract the x coordinate of both the points, we are going to solve these two curves. The point of intersection A and B are obtained by solving the two curves y equal to f of x and y equal to g of x. So solving of two equations gives us this. Therefore, area is given by integral of a to b upper curve minus lower curve of dx. Is how we identify the areas between two curves whose limits are not given, but we find them using the point of intersection concept. X coordinates are the limits of the given integral, definite integral.